There is a special case of dataset which makes interpolation impossible to compute with the same equation as the others. Learn it here in numerical solutions to C problems. Say that we have the dataset with x coordinates having an interval h of 1. The f of x values start with 1, followed by 2, then 6, 24, and 120. Commonly with regular x intervals, we create the Newton's difference table and then interpolate using either Gregory-Newton's forward or backward interpolation. Let's check Newton's difference table with the x and f of x placed on a table. For delta y, we get 2 minus 1 is 1, then 6 minus 2 is 4, followed by 24 minus 6 as 18, and 120 minus 24 as 96. Under the column for delta squared y, there are 4 less 1 as 3, 18 minus 4 as 14, and 96 minus 18 as 78. Then under delta cube y, there are 14 minus 3 as 11, and 78 minus 14 as 64. Lastly, delta raised to 4y has 64 minus 11, giving 53. With the first f of x as 2.8, we are going to use Gregory-Newton's forward interpolation, where the leading forward differences will be applied. For f of 5.4, having these located at the rear end of the dataset calls for the use of Gregory-Newton's backward interpolation, where the coefficients of the leading backward differences are used. Start with f of 2.8 through Gregory-Newton forward interpolation. We employ the standard equation as written, then identify y naught, the reference f of x, as 1 for the problem. Next is r, which is again the required x, minus the reference x over the x interval. This is denoted as x minus x naught over h, where from the problem, r is equated to 2.8 minus 2 over 1, giving r as 0.8. For the deltas, delta y uses 1, delta squared y is 3, delta cube y is 11, and delta raised to 4y is 53. Place these identified values into the equation and have the f of 2.8 as 1 plus 0.8 times 1, plus the next term as 0.8 times 0.8 less 1 upon 2 factorial times 3. Then the following term is 0.8 times 0.8 less 1 by 0.8 less 2 over 3 factorial, and the term is multiplied by 11. For the last term, there are 0.8, 0.8 less 1, 0.8 less 2, and 0.8 less 3 over 4 factorial, and multiplied by 53. Each term is then simplified as 1 plus 0.8 plus negative 0.24 plus 0.352 and add negative 0.9328. F of 2.8 comes out as 0.9792. If you go back to the table, this value of f of 2.2 is not within the range of 1 and 2. So before we answer why, let's try solving for f of 5.4. Since 5.4 is located near the end, We will use Gregory-Newton backward interpolation this time, and the equation is as written. Y of n is still the reference f of x, which in this case is 120. R is then the required x minus the reference x over the x interval, x minus xn over h. This is 5.4 minus 6 over 1, and that is negative 0.6. Neblas then start with 96 as nebula y, 78 for nebula squared y, 64 is nebula cubed y, and 53 for nebula raised to 4 y. Place all of these values into the equation and get f of 5.4 as 120 plus negative 0.6 times 96. The next term is negative 0.6 times negative 0.6 plus 1 over 2 factorial times 78. The next term has negative 0.6 times negative 0.6 plus 1, then negative 0.6 plus 2 over 3 factorial with 64. Then the last term has negative 0.6 times negative 0.6 plus 1 with negative 0.6 plus 2, then negative 0.6 plus 3 over 4 factorial times 53. These terms are simplified as 120 plus negative 57.6 plus negative 9.36 plus negative 3.584 plus negative 1.7808, which then can be reduced as 47.6752. These values seemingly within the range, but the fact that f of 2.8 is erroneous is a warning sign. So why did we get a rather odd answer for f of 2.8, which makes us doubt the answer for f of 5.4? This is because the values of f of x in the table increase exponentially, which means using a fourth degree function cannot be enough to represent the coordinates. This type of function is known as gamma function, one with exponential increase or change of values.